Today our main focus is going to be this concept called smoothness. And as I was... So anyways, we're going to talk about this idea called smoothness. So I find very often, like I was saying previously, that in a lot of CS circles, especially among students that learn analysis of algorithms, this topic is often glossed over. So I very often like to go into a bit more detail here, and you'll find that I'm showing you a lot of things that you may or may not have seen before. If you've seen it before, that's wonderful. If you've never seen it before, that's also wonderful, because you're going to be here to enjoy it here with me today. So let's get in on this. So before I can talk about smoothness, I have to talk about a concept about functions. And I may have brought this up previously. If not, one thing I need to talk about is the concept of an asymptotically non-decreasing function. So if I give you a function and I say it's asymptotically non-decreasing, which many functions have this property, especially the ones that we talked about studying last time. Many of them will have this property. So what is this? So if I give you a complexity function, so it's a complexity function is called asymptotically non-decreasing. Asymptotically non-decreasing if there exists n0 so that for all n greater or equal to n0, that f of n is less than or equal to f of n plus 1. So let me draw you a few pictures just to give this idea across. So let me draw a few pictures here. So just to make sure you understand the idea. So the big thing here is that there's going to exist a point where whenever I put in the input, it's always going to be that the next highest input is going to be going to, so if I have this input, I check if it's less than or equal to this other input, then it must be that when I apply the function to each, it has to be that the output of the function for that given input is less than or equal to the output of the function given the next input on integers here. So let me just give you a picture of what I'm talking about. So suppose I have, here's 3 different functions. So I got f, suppose I have f, g, and h. These are 3 different functions, and each of them, suppose I'm increasing its input n. So there's a lot of examples of asymptotically non-decreasing functions. So I'm just going to draw out some examples here. I mean, it seems something kind of like this last day. So notice here that this function, as an example, is the case. It is something we call a non-decreasing function. Notice that the function, whenever I put let me get my sticks out. Whenever I get my sticks out, I'm coming. So notice that if I look at this function, whenever I compare it against the next input, notice that it only goes up or becomes flat when I plot it out. It only goes up or it goes flat. Meaning if you plot it out, at least if we're talking about a function of this sort where it only has one input like this, it will go up or it will remain flat. So this is an example of what we would call a non-decreasing function. This right here, notice that the input, whenever I look at this function g, notice that the input always goes, so whenever I increase the input, the output always goes up. It never goes flat. This is an example of an increasing function. Here, however, notice that this one has a little bit of a stranger behavior, right? Notice that it goes up, it can come back down, but notice after this point right here and anywhere after this, notice that it goes up and it may even go flat. So the first example is of a function called a non-decreasing function. G is an example of an increasing function. And the third one is actually an example of an asymptotically non-decreasing function. So this one's non-decreasing. This one's an increasing function. We actually talked a little bit about that a moment ago. And this is an example of an asymptotically non-decreasing function. Some people call it an eventually non-decreasing function. It's the same exact thing. Asymptotically non-decreasing. But here's the thing. Here's the catch. That all of these are asymptotically non-decreasing. Believe it or not, all of them are. So if you just apply this definition, you look at this, say, okay, well, that there exists some point so that f of n is less than or equal to f of n plus 1. Well, look. I could just put n0 right here. So look, n0 is right here. And if I compare the input versus this next one, every time it either goes up or it remains flat, which is what this means. So it goes up or it remains flat. Notice that I could just pick n0 to be right here. I don't know, it's some integer. Say it's 1 in this case, that would be perfectly fine. Because imagine this is a parabola, for example. Then notice it only goes up after this point, never goes flat. But notice here that if I find out that n0 is right here, presuming the behavior of this function always goes up or remains flat after this, then notice that if I just care about what's happening after this point, this is also asymptotically non-decreasing, as I said just previously. But all of these are asymptotically non-decreasing. Does everybody see that? So it means that when you talk about non-decreasing, increasing functions, and asymptotically non-decreasing functions, all of these, including these other two categories, these are all asymptotically non-decreasing, meaning that we're talking about a large family of functions, especially, and that also will include all the functions that we've talked about up to this point. So this includes, so as examples, you can talk about, say, for example, a constant function, logarithmic functions are asymptotically non-decreasing, polynomials, polynomial, or exponential, for example. So the kind of functions we talked about before, these are all cases where you may find asymptotically non-decreasing functions. So that means that many of the functions that you're talking about when we talk about algorithm analysis, all are asymptotically non-decreasing. This is a helpful thing to know about. So all I'm going to do is I'm going to presume that all of these examples I gave you are shown to be asymptotically non-decreasing. And the way that you can do that is that you can, of course, for example, identify this n0 in a similar manner. It's not exactly the same. Most certainly, it's a somewhat different game plan. You would figure out what this n0 is, and then what you have to do is check that for all n greater or equal to n0, this inequality works. So that's the game plan. It's a little different. There's a lot of different analytical techniques for doing that, and I'm not going to focus so much on that here. That may get some treatment sometime in the future. But I hope that this is clear enough to you that all of these functions would be asymptotically non-decreasing. So that brings me to really where we're going with this, because we're not quite out of the gate when it comes to terminology, but most certainly we're in the scope of what I want to talk about. So there's certain functions, and similar to many of these, not all of these, but many of these, it'll be the case that the behavior of them is what we would call smooth, meaning that if I take sampling of the input, so if I take some parts of the input and I plot that out, and I look at the asymptotic behavior only for those inputs, It means that it actually can generalize over all the inputs. So in particular, there's a certain pattern or simplifying assumption that I can make where I can take a look at it, and the shape of the function is such that the differences between the samples I make, just as an example, versus the actual overall function, they are going to be similar enough by some constant amount. So that's kind of where we're going with this. So many functions are what we would call smooth. So you can use this fact in algorithm analysis to simplify the analysis you're performing for your algorithm. So that means that you can make you can actually just, instead of looking at like every input n when you're doing your time complexity analysis, you can restrict the input just to say powers of 2 or powers of 3 or powers of 4. For example, if you've learned about things like divide and conquer algorithms, you may actually have some familiarity with this idea if you've ever heard of something called the master theorem. The same kind of underlying theory is sitting underneath that. So what I would like to be able to do is I would like to know, or at least analyze algorithms, or suppose I get the complexity function, suppose that's f here. I want to be able to show you that f is big O of g, but so suppose that I want to have the ability, because say, for example, like I was mentioning a little earlier, suppose that it's really hard to, or it gets really ugly to do the analysis for all inputs n, because say the numbers don't cleanly divide each other. Say, as a common example, it might be something like your favorite case of like merge sort or binary search, where, for example, the input may not cleanly divide into 2 equal parts. It may be the case that it might be like the ceiling or the floor of halves. I would like to be able to have it where, for example, I can make presumptions, so I can restrict or simplify what n is. For example, the one that I'll focus on here is when n is a power of b. A power of b. And this is some fixed integer constant for us. So what I'm saying is that it would be that n is equal to b to the power of k for any k greater or equal to 0. So what I would like to be able to do is, under such a simplification, I want to be able, and like I said, this is the good kind of cutting corners, because what I'm going to show you is that you can make this simplification and you can still end up with the overall result that you want to desire, even if you're only analyzing this for this specific set of inputs. What I want to be able to do is show, if I have this, I want to give you some condition. So there's some stuff in here that relates to this idea of smoothness, such that I could just simply say that f is big O of g, unconditionally. So what you could do is you could do your analysis with the smaller restricted inputs, so like n is a power of 2 or n is a power of 3 or something like that. And I want to be able to do this with some conditions in place. I can automatically get, as a result, that f is big O of g without ever having to actually go and consider all the inputs, because all of the heavy lifting is done by this concept of smoothness. So there's going to be some condition, which we're going to talk about, that's going to give us this ability to go from this simplified analysis. So very often you'll run into this when you're doing algorithm analysis. Sometimes people say, well, assume n is assume without loss of generality that n is a power of 2, for example. It's very common that happens. Now, they may not necessarily be using smoothness, but this is one vehicle for allowing you to do such things without losing any generality, because the smoothness of the functions allows it to happen. That's not the only reason why somebody can get away with that. For example, the analysis itself could be simple enough that you can easily just simply have it where whatever their analysis is doing is always accounting for more, say if you were to cleave it up or down, for example, if you're breaking into halves. I just want to make the remark that sometimes it's unclear if they're using smoothness or not. But I just want to make it clear that yes, you can get away with some neat things using this idea of smoothness. But I just wanted to tell you that this like secret little trick that some computer scientists are using when they do time complexity analysis or different kind of analyses, and smoothness allows you to kind of smooth out these issues. But I'm saying that it isn't the only way you can do things like this. That's what I'm saying, is that there's just some conditioning here that allows you to do this. We're going to talk about one of those. I hope that is clear, everybody. So, that being said, let's talk about what the heck is all of this about. So, I'm going to define something called smooth. And I must stress that it does technically have also a stronger definition based on what we call big theta notation, but I'm not talking about that here. So a complexity function. So if I want to talk about a smooth function in this context, I'll say a complexity function f that is both, so it has to be both these things. It has to be both. The first thing is that it's asymptotically non-decreasing, which we've just already talked about. And two, it has to be that the following is the case. And this is why in Big O Bootcamp, why we'd be interested in this, is that f of 2n is big O of f of n. So what the second condition is saying is that if you look at the input, so whenever I give you an input n, if you multiply that by 2 inside of the function, so whatever the input is twice that, it has to be that this is big O of f. So I'm going to do some examples with you to illustrate the idea of smoothness, what a smooth function is. So I'm just going to need another marker here. So as I said, all the functions we're going to study here are asymptotically non-decreasing, just to be clear. So I'm not going to focus so much on that here. I'm just relying on your understanding of how these different functions we talked about work. So I thought I would do a couple examples to really warm us up to this idea. So for example, I told you, so if we talk briefly about constant functions, you can actually show that constant functions are smooth. So constant functions. So suppose I give you f n is equal to d, where d is just some positive integer constant. So what we're going to do, so we already talked about how these are asymptotically non-decreasing, so I'm not going to focus on 1. Instead, I'm going to focus on 2, that second condition. So what we're going to do is I'm going to walk you through the process of proving using the definition of big O, the second condition. So as usual, we have the game plan. I tell you what I'm going to do with our proof, okay? So we find constants. C, which is a positive real number. And n0, which is a positive integer, right? Such that for all n greater or equal to n0, it has to be, remember, all we're doing, remember, our goal is to show that f of 2n is going to be less than or equal to c times f of n. So I'm just going to plug that in here just to write it out directly for you, but I'll write its equivalent counterpart here. So f of 2n is less than or equal to c times f of n, which this, for our case, this we're going to be talking about d is less than or equal to c times d. Well, this should remind you a lot of the very first example we did last time. So notice that it's just, we're playing lookalike again. So notice that, wait, no, it isn't just this, right? Notice it isn't just this, or is it? It's 2 times n. But notice that n doesn't appear anywhere in the function. So yeah, it is that d is less than or equal to c times d. So remember, whatever is the input, you would write 2 times that for wherever n appears in the function's computation, right? But notice that here is just some constant. So 2 times the input doesn't make any difference. It's still d. So this makes it easy for us. So I'm just going to pick c is equal to 1. And normally here I would say that, oh, we're going to find n 0, but notice that it's a constant function. There's not very much interesting going on here. So then notice that both sides of the inequality are equal, right? Both sides of the inequality. That u is looking a little bit spicy, I guess. It's got a little hook on it. Somebody let them know about having a good day, okay? Both sides of the inequality are equal for all n are equal to 1. So that means you just choose n0 is equal to 1, and then you're done. And now we just have to invoke the definition of big O, and we're piece of cake, right? Therefore, by the definition of big O, D is big O of D, right? And function f of n is equal to D is smooth. And we're done. Because remember, we already know about the first condition. That's okay. That's okay. So I thought this would be helpful to get an idea of what I'm doing here. So it's just another big O claim. That's all it is. So I'm going to do, let's do 2 more examples. Just I want to make sure it's very clear how this works. It's a little it's a slight tweak of what we were doing last time. So here's another example. Let's prove that log base 2 of 2n, so I'm just going to put the second condition right here. I'm going to show you that this is big O of log base 2 of n. So remember, this is the second condition if I want to show that log base 2 of n is smooth. So we already established, we already know that logarithms are, in fact, increasing functions. So log base 2 of n is an increasing function. It always goes up. It just slowly grows. But it indeed goes up if you plot it out. So that indeed makes it an event asymptotically non-decreasing. So if I prove this property right here, that means that log base 2 of n is smooth. So let's write out a proof for this. So walk through the same process. Let us find constants. Constants c, which is a positive real number, and n0, which is a positive integer, so that log base 2 of 2n is less than or equal to c times log base 2 of n for all n greater or equal to n0. Give me one moment. I'm just going to grab another marker. It seems like I have a sort of playing Russian roulette with the markers at this stage, but let me just fling this off. It's gone. It's gone. Just get some more markers here. Okay, here we go. So this is the game plan that we have, and I would like to show you that, remember, the goal is to show that log base 2 of 2n is big O of log n. So I just have to find these 2 constants, right? That's the goal. So you might say, Dan, what are you going to do to make this happen? Now, here's something that's neat. Now, you may or may not know this about logarithms, but when you have a product inside of a logarithmic function like this, there's something you can do to that input. Notice that it's 2 times n. Does anybody know what I can do to that logarithm there? Any tips on or tricks that anybody is aware of that maybe we could do with that logarithm right there? So I'll tell you that there's a property that logarithms have over products like this. If you're unsure about what I'm referring to, just try writing out what logarithm means, like what's the definition of a logarithm, in terms of writing it like exponents. So if I have a product inside there, it's the same as me doing something. So I'll start writing it, and if you have any ideas, just let me know. Notice that by the product rule of logarithms, or product law. Oh yeah, this marker is much better. Product rule of logarithms, which I'll remind you of in a moment. We could say the following. So watch this. Watch this. So remember, we're dealing with this inequality right over here. So let's write on over here what we could do with this. So here's what we could do. So watch this. Well, remember we have on the left-hand side log base 2 of 2n. Well, log base 2 of 2n. Well, this is just equal to log base 2 of 2 plus log base 2 of n, right? So you could distribute products inside of logarithms over addition. But what's log base 2 of 2? Well, let's think about it. 2 to the power of what is equal to 2? 1 plus log base 2 of n. But this, notice that, remember, we talked about what an increasing function is, right? Well, for what values is 1 going to be bounded from above, or I guess technically you'd be allowed to be equal to it, to the log base 2 of n? Well, I'm going to do the following. I used this trick last time. I'm going to replace 1 with log base 2 of n plus another log base 2 of n. And I'm allowed to do this because log base 2 of n is greater or equal to 1 for all n greater or equal to 2. And this is because logarithms are increasing functions. So just don't forget that fact. So don't just blindly think about this. Remember, we're working under the prism that we understand that logarithms are increasing functions. So this is the reason why I can do this. But this is just equal to 2 times log base 2 of n. But this, remember, this all is true for all n greater or equal to 2. So just keep that in mind. So when I wrote this out over here, I should say for all n greater or equal to 2. So now what am I going to do now? Well, let's think about it. This is just, well, look, if I make c is equal to 2, so I'll say by picking, c is equal to 2, and n0 is equal to 2, the above inequality is satisfied, right? Because that's what we get right here is the right-hand side of such the inequality, which is the same as the one I had in the previous sentence. Therefore, by the definition of big O, log base 2 of 2n is big O of log base 2 of n. And we're done. So we just use that one property of logarithms to make this work. So are there any questions about this? Yeah, this one seems pretty slick. If you understand that one property about logarithms, we're pretty good. So I thought next I would do one more example, just illustrating the second property of what a smooth function is. I'm going to show you that a polynomial of the form n to the power of k is also smooth. So one thing I do want to stress as I'm going through this, like I said, the definition of a smooth function can be defined in terms of big theta, which is something I have not discussed here. But I must stress that the game plan is very similar. It's just that you need to understand within that prism. But anything you can say about big theta also has to be true for big O. So that's why we're sticking with big O here. So let's do another example. Let's prove that 2n to the power of k is big O of n to the power of k for any constant k greater or equal to 0. So if we can prove this, and remember, we know that polynomials like of this form are asymptotically non-decreasing, this would mean that polynomials of this form are also smooth. So here's the proof. So we're just going to walk through the same process again. So to prove the claim, we find constants. We find constant c, which is a positive real number, and n0, which is a positive integer. So that for all n greater or equal to n0, 2n to the power of k is less than or equal to c times n to the power of k. Now here's where it gets a little fun. Now, this is where sometimes it's actually really important to know the difference between a variable and like a constant. So we have names for these different variables, but some of them are allowed to vary. Some are fixed. They are constants, such as k. K is a constant. 2 is a constant, right? Well, what I'm going to do is I'm going to make a constant, and at first you're going to be like, Dan, what are you going to do to make this work? Because it's 2n together raised to the power of k, and then I have c times n to the power of k. Well, watch this. Watch this. Sorry, I'm getting very excited about this. Well, I'm going to make a really big constant, okay? Well, because remember, k can be really big. This is a claim involving any constant k. So I must stress that if k is big, this is also going to be a big constant. I didn't say that all of these constants end up being nice and simple. Like, they're very easy to write down, but they might actually be pretty big. This constant is going to make this proof go a lot smoother. So I'm going to pick c to be 2 to the power of k. You might say, Dan, why would you do that? It's because I'm going to make something that looks similar to the left-hand side. Remember, I'm just playing look-alike. So now we would find, so I would normally write right here that we're going to find some n0 such that that inequality is true. But I'm going to use the following property of exponents. By the power of a product property. Now, for those that are not acquainted to this property, it works like this. So I'll just write it off to the side here. What it says is that ab to the power of m is equal to a to the m, b to the m. That's what it says. So what I'm doing is I'm applying the exponent to each separate thing it's being multiplied by. So I could just simply use this, right? So by the power of the power of a product property, which I'm going to stress, remember, like I said, it's this. All I have to do is now do this. And you're going to notice it's going to be a lot smoother. Pun intended, okay? Notice that both sides of the equal, both sides of the inequality to n to the power of k, and all I'm just going to do is I'm going to apply that property, which, remember, this will just end up being the right-hand side to the power of k times n to the power of k for all n greater or equal to 1 are equal. So now all I have to do, well, I already know what n0 should be. It should be 1, right? So choose n0 is equal to 1. Therefore 2n to the power of k is big O of n to the power of k. And we're done. So with this proof, now you know that polynomials, so if I could show you this involving n to the power of k, then you know it's smooth. So if you have a complexity function, it gets categorized by big O of n to the power of k, you could say that n to the power of k is smooth. This will be a very lovely property for us to have at our disposal. But I must stress that not every function is smooth, just to be very clear. So I should say that not every function is smooth. So just as an example, suppose I give you f, where it's going to be 2 to the power of n is not smooth. So if you want to see why this is the case, in my notes I'm going to have the proof for this. It's a contradiction proof. Remember the game plan when we show big O claims, we find those two constants, right? Well, the way this would work is that you show me that these two constants can't exist. So yeah, so not every function is going to be smooth. We've seen that constants, logarithmic functions, polynomials are all smooth. And these are very common ones you'll run into when you're doing time complexity analysis, which is nice. That's wonderful. So all the main ones that you've seen, and there's other ones too, like n log n is also smooth. Most of the ones that you're familiar with are smooth, but some of them, like I said, if you tried sampling their points for, say, by a multiplicative constant like this, you'll see that the gap is going to be too wide, such as with an exponential function. But I'm not going to get too much into the intuition around that. But now we've seen some properties that we can have when it comes to, like, okay, we know what a smooth function is. I'm going to need some more terminology to make this work.